All right, here we go, kiddos. Section 4, Chapter 5. Quite possibly the most important mathematical theorem you will ever come across, the Fundamental Theorem of Calculus Part 1. And it's really an interesting theorem. It does a lot of cool things. And basically, here's what it says in Math Ease. If a function f is continuous on a to b, then the function capital F of x is equal to the integral from a to x f t dt and has a derivative at every point x in the interval a to b. And the derivative of capital F is equal to the derivative of the integral, which is equal to f of x. Now what? Let's take a look. Well, let me just grab my handy dandy calc book here. There's a couple things in here I want to share with you about this that are really important. Number one is all of this started back with Newton and Leibniz. And that's where the calculus comes from, and that's where this theorem comes from, and all the stuff that we do comes from those two guys kind of working independently. And it's possible that maybe one of them borrowed a lot from the other, but you know, it's not been documented very well. And so here's the deal. The first part, which is this guy, this first part says that the definite integral of a continuous function is a differentiable function of its upper limit of integration. Okay? And then it tells us what that derivative is. All right, you might need to back up and rewind that again. But what we're saying is, if we got a continuous function, we can integrate, and that upper limit of integration becomes the differentiable function. How does that look in real life? Okay, well, let's check out this cool cat right here. Find d dx of the integral from negative pi to x of cosine t dt. So we're going to use the fundamental theorem of calculus right here. And notice what it says is f of t d, if I go from some lower limit to a variable upper limit, so from a to x f t dt, then what I'm going to do is just simply replace these things, and I'll get the function that I'm interested in. I'm taking the derivative of this integral, and so what's going to happen? This is going to happen. Cosine x. That's what this guy becomes. Everywhere you see t, you just replace the t with the x, and you're good. Well, okay. What about this guy over here? d dx of x from 0 to x of 1 over 1 plus t squared dt. Again, what you do with this guy is you replace the t value with the upper limit of integration. We're taking the derivative of the integral from 0 to some upper limit of integration, which means that that limit is sliding wherever we need it to go. All right? And when you do that, the fundamental theorem of calculus says this guy's going to be 1 plus x squared. It's really interesting. And you may have to just do what I do for a little while and work these problems out exactly how I've worked them out before you finally kind of start getting, oh, this is really what's going on with this. Don't make this a really super difficult, super hard issue. The fundamental theorem of calculus is an important theorem, and it's full of math lingo that you may or may not get the first time you see it, but keep working on these guys, work these problems like I'm working these problems, and eventually it'll start to click into place of what's going on. All right, second example of chain rule, but notice this time instead of starting at 1 and stopping at some value of x, we're stopping at some value of x squared. So real quickly, let's try and remember our fundamental theorem of calculus says that if we take the derivative of the integral something that looks like this. This is just a real quick example. Fundamental theorem says that this is going to become x squared plus x, okay? But the difference between these two problems is the x is the upper limit of integration, and the x squared right here is the upper limit of integration. So what we're going to do is we're going to make a substitution with u, and this is really similar to the chain rule that we used in the first semester. So what we're going to say is that u is going to be equal to x squared, and that du dx is going to be equal to 2x. So we're going to work with the integral from 1 to u of cosine t dt But now what we're going to work with here is the chain rule issue. And so if I change this u up here, I can't have dy dx. Remember that dy dx, if we go all the way back to chain rule, and chain rule is a little tricky, but dy dx is going to be the same thing as dy du times du dx. So what we have to work in then is this du dx and the dy du. And so the dy du is this part, the du dx is this part. So what we're going to do is we're just going to say, hey, this guy, d dx of this, okay, times du dx. And this should be d dy. d dy of all our u's times du dx. Well, we can do this guy. This is just going to be cosine of u, and then times du dx, which is going to be 2x. And so when we finish this problem up, we just replace our u with what we set it equal to. So this is going to be cosine x squared times 2x, or 2x cosine x squared. And that x squared is inside the cosine. It's part of the whole cosine process. So there you go, chain rule with fundamental theorem. Okay, let's look at a couple of more integrals using fundamental theorem of calculus part 1. Part 2 we're going to use a lot and we're going to love it. But part 1, here we go. It's a little bit more tricky. Remember that if I just work out a real quick one here, I'll just set it up and work it out really fast. If I go from 0 to x of t squared dt, and I take the derivative of that, then what I end up with is x squared. Okay, that's what I end up with. Well, if you'll notice right off the bat with this first guy right here, the x is on the bottom and the 5 is on the top. Well, not a big deal. Remember that one of the things that we learned from our properties of integrals is that we can trade around these upper and lower limits of integration. And if we trade places, we just put a minus sign in front. So what if we looked at this? Y equals negative, and then the integral from 5 to x of 3t sine t dt. Now we can just use the fundamental theorem just like we've seen in the past couple of slides. We're just going to apply the whole derivative rule. So if I dy this guy, if I dy that whole guy, take the derivative of the whole guy, what's going to end up with is negative 3x sine x, and that's all there is to it. It's pretty user friendly. Now look over here on this guy. We go from 2x to x squared, but how is that going to work? Now we've got variables on both sides. Well, one thing that we can do is we can split this up. And we can write it as two separate integrals. And again, it'll be using some of those rules. So we don't know where x goes or starts or stops or anything like that. We just know that it's always changing. And so what if I split this integral up into two integrals? Something like this. From 2x to 0 of 1 over 2. Whoa, that's a bad looking 2. 2 plus e to the t dt. Plus the integral from 0 to x squared of 1 over 2 plus e to the dt. Now, if you'll look at these two guys, what we have is a situation where we're taking one integral, adding it to another integral, but we're getting the entire integral that we originally starting with. because we go lower limit of 2x to 0, and then picking up right where we left off at 0 and going to x squared. So we get all of those values of x in between that we have to have. The problem is, now I've got this 2x on the bottom. Well, the first example that we did today fits this situation perfectly, where I can actually work with the negative integral from 0 to 2x of 1 over 2 plus e to the t dt plus the integral of 0 to x squared of 1 over 2 plus e to the dt. Now, the only other thing that we've got to do here is use our chain rule, because we don't have just plain old x up there in our upper limits. So if I let u equal to x, if you rewind back to the previous slide, we talked about chain rule. So basically what I'm going to do is multiply my integral by the derivative of 2x, which would be not du, it would be du dx, which is equal to 2. And on this other side over here, we would let u equal x squared. And so we would multiply by the derivative of that. So du dx is equal to 2x. And really, that's all we're going to do. And the t becomes the 2x, and we multiply the whole thing by 2. And the t becomes x squared, and we multiply the whole thing by 2x. So what does this last guy look like then? Well, I'm going to have, when I take the derivative of this whole thing, d dy, of this whole thing right here, what I'm going to get is negative 1 over 2 plus e. And then instead of a t, I've got to put my upper limit of integration. Remember, that's what the u is, times 2 plus 1 over 2 plus e. And then again, my upper limit of integration right here, where the t is going to be this x squared times 2x. Let me move that over a little bit. Because that's the derivative part. And so you're going to get a really wacky answer here, and that's okay. Here's your answer. Negative 2, and these could be in either order as long as the signs are the same. 2 plus e to the 2x plus 2x over 2 plus e to the x squared. And that's it. Now this looks really wacky, but it's not a big deal. Just be patient, watch this video, watch the one right in front, and you'll see that there's just some really simple steps that we do to work through this complicated problem. All right, so here we want to find a function y equals f of x where the derivative dy dx is equal to tan x, and it satisfies the condition f of 3 equals 5. Well, let's just have a real quick recap of fundamental theorem, and that says this, that if I have d dx of something from, say, 0 to x of t squared dt, that this is going to give me the derivative x squared. So to get this part right here, dy dx equals tan x, I could let y equal the integral from 0 to x of tan t dt. And if I take the derivative of this, when I take this derivative, so if I run over here, d dx of the integral from 0 to x of tan t dt, this is going to be equal to tan x, okay, tangent x. So I just need an equation now, though, that satisfies the condition f of 3 equals 5. F of 3 equals 5. In other words, my x value has to be 3, and when that happens, my y value is 5. These are the rules that I need to follow for this guy. So how does that change what I've got here? Well, my answer then develops from where we started, and I need that x value to be 3. So what I'm really going to be working with is the integral from 3 to x of tangent t dt. Why 3 to x? Because 3 is my value of x that I have to have. The other thing it says is I've got to have a y value of 5. When x is 3, y is 5. And to handle that aspect of it, we can put a plus 5 back here. Now think about this. If I take derivative of all of this stuff, derivative of 5 is 0. And the derivative of this part right here is going to be tangent x. So this equation works. And now the moment you've all been waiting for, the Fundamental Theorem of Calculus Part 2. Hey, we've already done this one. It's where you take the capital F derivative function of b minus capital F of a, which is equal to the integral from a to b of fx dx. We've done this, but it's actually part of the Fundamental Theorem of Calculus. It's the second part of the Fundamental Theorem of Calculus. And it's a way for us to solve an integral out, a definite integral, by undoing what's being done. It's really kind of cool, and we've done it several times, but here we go. Let's just do another problem because, hey, what else are we going to do? So I've got this guy right here, and we're going from -1 to 3 of x cubed plus 1 dx. Now, we could look at this as two separate functions, but I like to look at it kind of as one. It's a little bit easier and less messy. So here we go. If y prime is equal to x cubed plus 1, y is equal to what? Well, remember when you take derivative, you subtract 1 from the exponent, okay? So if I have x cubed as my derivative, I had to start at x to the 4th, all right? And right here I have x to the 0 as a derivative, so I had to start with x to the 1st. Now, just ask yourself, 4 times what number is 1? Because that's what I have right here. So that's got to be 4 times 1/4. And 1 times what number is 1? Well, that would be 1. Okay. So this guy right here is capital F of x. This guy right here is little f of x. So what we're doing is we're evaluating the integral by finding the antiderivative of little f of x. And now what do we do? Well, now we take this 1/4 x to the, whoa, that's not the color I want. Hold on. Now we take this 1/4 x to the 4th plus x, and we evaluate it from -1 to 3. And what's the evaluate part? That's this guy right here. We're going to do the function where we stop minus the function where we start. So where do we stop? We stop at 3. So this is going to be 1/4 times 3 to the 4th plus x minus the function where we started. 1/4 times -1 to the 4th plus -1. Okay? So it's the function where we stop minus the function where we start. And we just simplify all this out and we'll have ourselves an answer. So I've got 81, 3 to the 4th is 81. So this is 81 over 4. This guy right here that I wrote down as x is really not x. I was just tricking you. So let's get rid of the trick. That should be a 3. So 81 plus 3 minus, what's going on here? 1/4 times 1. 1/4 minus 1. Okay, so this is what we've got, and you can put all this together into one. You can punch it in your calculator. You can reduce your fractions. You can do whatever. But this is basically going to be 3 plus 1, okay, which is 4. And 81/4 minus 1/4, which is 80/4, which is 24. How cool is that? And the other thing that you could do is punch this into your calculator, and there's 2 different ways to do that, or 3, a myriad, there's thousands, okay? I'm going to show you 3 different ways that you can punch it into your calculator. I'll do that on the next clip, and you can see what happens depending on which calculator you've got or how you want to mess with it. There's some you got some choice. Okay, so with that said, that's Fundamental Theorem of Calculus Part 2, and it really is super handy. All right, so here we're going to use the TI-84 calculator, and I'm going to show you two different ways on the 84 here that you can evaluate the definite integral. And for the 83, you're going to want to use the graphing part. It's probably the easiest one, okay? If you've got an 84 with map print, if you hit alpha window, what that does is that brings up a list of different options that you can go to. So it's technically the F2 key, all right? And if you'll notice in there, we've got a finint, the finint button, okay? Function integer. So go ahead and choose that guy, and it gives you a template to fill in. So, hey, we're just going to go from -1 to 3, and whoops, that needs to be -1. Sorry about that. So we're going to -1 to 3, and then we can just type in our equation, x cubed. So x cubed plus 1, and then over here dx, and then boom. There it is, 24, which is what we found out on our previous slide doing it with antiderivative. The other way you might do it, and if you'll just pause for a second while I get in here and change a setting. The other thing that you could do is if you have a TI-83, this is an option for you. You're going to hit the math key, or if you have an 84 without math print, hit the math key and look down here, option 9. Option 9 is finint, okay? Finint. So go ahead and pick that. Now, it looks totally different, but we're going to do basically the same exact thing. So here's the rules. Anytime you're on an 84 and it comes up with this. Function, comma, variable, comma, lower limit, comma, upper limit, enter. That's what it's going to be. So that's what we're going to do. So what we're going to do, what function are we working with? We're working with x cubed plus 1, so it would look like this, comma, the variable x, comma, from -1, comma, to 3, enter, and it's 24. So if you have an 83, this is how you're going to do it. Now, there's one other way to do this, and it's really cool, and it's actually the easiest way for the 83s. On the 84s, you could do you still have choices, okay? So let's graph this guy, x cubed plus 1. We're going to graph this guy, x cubed plus 1. And I'm just going to go with zoom 6, which is a standard window. It's not always the best window to use, okay, because everything is squished funny. It's stretched wider and it's squished vertically. So it's not technically a true shape, but it lets us see what's going on, okay? Now, if you're on an 83, if you hit the second, or the 84, okay, if you hit second trace, it'll take you to the calc menu, all right? And then right in there is the integral. Choice number 7 is the integral. So you can hit choice 7, and it asks you for the lower limit. Just put in -1 and hit enter. And then it'll ask you for the upper limit, and you put in 3 and hit enter. And then boom, it does this part for you. Now, you have to be able to see the lower and upper limits on the x-axis on your calculator, or you will get an error. So if you can't see -1, or if you can't see 3, or whatever your limits are for your problem, change your window so that your upper and lower limit are both on that window. And then you can graph it, and here you go. What's the answer? 24. All right, so let's look at a couple different ways that you can find the definite integral on your TI Nspire. So if you've got an 84 at this point in time, tune out, all right? Or go get an Nspire, because they're pretty fabulous. So what we're going to do is we're just going to go ahead and go into the calculator part here and pick that guy. And then if you'll hit the button right next to the book, it brings up like this template of all this stuff going on. Well, if you'll notice down here, bottom row, we got a definite integral template. And then we just put in -1, and then we put in 3, and then we put in, our x cubed dx all that junk right there. So +1. And then over here, put your variable that you're using, which is x. And so there it is. And 24 is your answer, which is what we got using antiderivative. So there's one way you can do a definite integral on your calculator. Now, if you really want to see what's going on, another thing that you could do is if you'll just hit the Control I button, hit Control, hit I, what it does is it inserts a new slide. And then let's pick a graph here. And let's graph this guy. So F1, what do we want it to be? We want it to be x cubed +1. And so we're going to graph this guy, and here it is right here in all its glory. Now, just like on the 84s and 83s, we can find the area under that curve. So if you'll come to graph and then analyze, look, we've got integral, and it even says the word integral. So there's no mistaking what's going on. Just choose it. It asks you for the lower bound. You can either use your finger and slide around, or you can just say, hey, I want to go with -1 and hit enter. And it asks you for the upper bound. We're going to say 3 and hit enter. And boom, 24 is right there. Let me move this guy out of the way. All right, so there you go. You can see that the shaded area is 24. That's our integral evaluated from -1 to 3. And just like with the 84 and the 83, on the Nspire, the calculator graph needs to show on the window that you're looking at the entire interval from your lower limit to your upper limit of integration. So if those numbers aren't visible, if -1 wasn't visible, or if 3 wasn't visible on the x-axis, we would get an error message, okay? When that happens, just hit the menu key, choose window, and adjust it so that the entire interval is visible. And there you go. There's using your TI Nspire to find the definite integral. So what we've done up to this point in time is we've taken all these definite integrals and we've evaluated them, and we equated the evaluating of the definite integrals with area under the curve. So if we had some sort of geometric shape, we could evaluate the integral. And then we learned about the fundamental theorem of calculus and how we could evaluate integral with antiderivatives. And so now what we want to do is we actually want to use integral for one of the things that it allows us to do, which is to find the area under curve. Now, areas under curves are interesting, and with integrals, we really have to pay attention. Because if I ask you to evaluate an integral, it's totally possible to get a negative number. It would take the area below the x-axis and add it to the area above the x-axis. And if we evaluate that integral, we should get a negative number. But if we're asked to find the area between a curve and the x-axis, that's like asking for a distance traveled. And distance traveled will always be positive. So if we're asked to find area using the antiderivative, find the area between the curve and the x-axis. Wow, what was that? So here we go. Here's what we're going to do. We are going to put together a real quick x and y axis to have an idea of what our graph looks like. And free OCD kids, if this isn't 100% straight, I'm really sorry. I am not that OCD anymore. I mean, I used to be. I might still be a little bit if you really know me. Okay, so here we go. 4 minus x squared looks like this. 4 minus x squared looks like this right here. And what we've been asked to do is evaluate the integral from 0 to 3 of 4 minus x squared. Now, pause the video, punch this into your calculator real quick, and then come back to the video and just in your mind, look at your calculator and then think about what I'm getting ready to tell you. Okay, ready? Pause. Okay, what'd you get? Did you get a big answer that you thought you were going to get? Did you get negative? What'd you get? Okay. What your calculator did was it said, hey, I'm going to start here at 0, and I'm going to go all the way over here to -3. Or I'm sorry, +3. And I'm going to add up this positive area with this negative area. And so if you look at your calculator, what it's doing is it's combining both of those together. So it's going to do positive minus negative. But if we're asked to actually find the area under the curve, what I need this total area here. I need absolute value of this area and absolute value of this area. Okay, what does that tell us? It tells us that we're going to actually break this integral into two right here where it crosses the x-axis. And, 4 minus x squared, what number? 2. So what we're going to do is we're going to look at the integral from 0 to 2 of 4 minus x squared dx. And we're going to add it to the integral from 2 to 3 of 4 minus x squared dx. That gets us the same information that we're interested in. Okay? But here's the kicker. The one change that we're going to make on both of these, because we want total area, that's like total distance. It's always going to be positive. It's like absolute value. Hey, absolute value, absolute value, absolute value. We want the absolute value of these puppies. All right. Now, we're not going to actually integrate absolute value. That's going to be another lesson for another day. But when we evaluate these guys, we want the absolute value. Okay, so I'm just going to get those absolute value lines off. We're going to evaluate real quick. So this is going to be with antiderivative 4x minus x cubed over 3. There's your first guy. Evaluate that from 0 to 2. Plus, and then it's the same integral again. 4 minus 4x minus x cubed over 3. And we're going to evaluate this guy from 2 to 3. Okay. And when we get to the actual evaluation process, that's where we're going to look at the absolute values. So here we go. I'm going to have stop minus start. So 4 times 2 minus 2 cubed over 3. I want the, minus, and then 4 times 0 minus 0 cubed over 3. There's the first guy right here. And so this is going to, these are zeros, right? Those go away. 0 times 0 divided by whatever, doesn't matter. These are all zeros. So over here I've got 8 minus 8 cubed. Okay. And that's going to be, if I put this over 3, this is going to be times 3, 24 minus 8. So 16 thirds. I want the absolute value of that guy. I want absolute value right here. This area right here is absolute value 16 thirds. I want that. Okay. Then let's evaluate this second part right here. And I'll just do that right here. So that's going to be 4 times 3 minus 3 cubed over 3 minus, and then where I started, which was at 2, 4 times 2 minus 2 cubed over 3. And hey, these guys right here, look, you see anything similar, right? So this is 16 thirds. And for 12 minus 9, okay, 12 minus 9 is 3. So if I get a common denominator, I'm going to have 9 minus 16, which is negative 7 thirds. Okay, I need the absolute value of this because he goes right here. That area is negative 7 thirds. But in order to get total area, I need the absolute value of that. So here we go. 16 thirds plus the absolute value of negative 7 thirds. Whoa. Let's see here. Absolute value negative 7 thirds is going to be 16 thirds plus 7 thirds, which is 23 thirds. So if you're asked to find area, use absolute values. If you're asked to evaluate the integral, then you just do your addition and subtraction just like you learned in second grade. All right, now we're looking at a problem where we're asked to evaluate using our calculator the total area under a curve. And the problem they gave us is x cosine 2x. So we're going to just graph that guy and make sure that when you graph this guy that you are in radian mode on your calculator. If you're not in radian mode, you could get some really wacky graph and your numbers won't quite sync up correctly. So I'm going to go ahead and use TI Nspire. If you want to see how to do this on a different calculator, you can just go back and get a refresher from one of the earlier lessons. Okay, so we're going to add a graph, and on this graph we're going to have x times cosine 2x and we're going to look at this graph right here. So there he is, and he's pretty intense looking, pretty intense. Now what we want to do is we want to find the area of the region between the curve and the x-axis from -3 to 3. Well, if you'll notice on this graph, I've got area above x-axis, I got area below x-axis, and if I'm looking for total area, what happens with this is they cancel each other out. You know, so if I'm above here and below here, that would be 0, and then above here and below. So I want total area, which means that I need absolute value. So I'm just going to come back to my function. If you hit Control G, you can come back in here to your function. And what I'm going to do is I'm going to put in ABS, which means absolute value. And then I'm going to do a parenthesis right here and watch my graph change. Boom. Now everything's above x-axis. This now gives me the opportunity to evaluate this integral for total area, which is different than evaluating the integral to evaluate the integral. So what are we going to do? We're going to go to our menu key. We're going to choose to analyze the graph. We're going to choose the integral, and then we're going to tell it, hey, we want to start at -3 and go to +3. And you need to make sure that everything is listed on your x-axis. If the lower and upper elements are missing on your x-axis, you've got to change your graph window so that you can see all them. And what do we get for our total area? It should be positive. If it's not positive, then you've got an oops in there somewhere. Everything should be above x-axis. So in this case, I get 5.43. And there you go. Finding total area using your graphing calculator.